America built bridges, docks, and railroads on ground too soft to hold them by hammering thousands of timber piles deep underground. Steam pile drivers made it possible, lifting massive iron hammers and dropping them again and again until the earth finally held.
Imagine standing beside an American waterfront in the early 1900s. Above you rises a wooden tower taller than a house. Suspended inside it is an iron hammer weighing several thousand pounds. A steam engine pulls the hammer upward, then releases it. The weight crashes onto the top of a timber pile. The ground shakes, steam hisses. The hammer rises again and drops again. Each blow drives the timber farther into mud that seems far too soft to support anything. But eventually, the pile stops sinking. Builders cut off the top and drive another beside it, then another. Hundreds of them might disappear below a bridge, railroad trestle, warehouse, or pier until an entire structure is standing on a forest nobody will ever see. This was the steam pile driver. Its mechanism was brutally simple. Lift something heavy, drop it, repeat. Yet machines based on that idea helped America build where solid ground barely existed. And the strangest part was this. The piles did not always need to reach solid rock. So what exactly was holding everything up? Buildings are heavy. Bridges are heavier. And waterfront infrastructure creates an especially difficult problem because the ground beneath it may consist of loose sand, saturated clay, silt, or mud. Put enough weight directly on weak soil, and the ground can compress. Foundations settle, structures tilt, bridge piers shift. A dock built at the edge of deep water may have almost no firm surface on which to stand. But American expansion kept demanding construction in exactly those places. Ports needed wharves extending into harbors. Railroads crossed wetlands and rivers. Factories appeared beside waterways because ships and barges carried raw materials. Bridges required supports in riverbeds. The easiest location for transportation was often one of the worst locations for foundations. Engineers had an old solution: drive long columns called piles into the ground. Timber was common because it was strong, relatively cheap, and available in long, straight sections. The problem was getting it deep enough. A 20, 40, or 60-foot pile did not slide politely into the earth. Someone had to force it down. And before steam, that job could consume an extraordinary amount of time. The pile driver itself was not a new invention. The basic principle had existed for centuries. Builders erected a tall frame above the pile. Inside that frame hung a heavy iron or stone weight, traditionally called a ram or sometimes a monkey. Workers hauled the weight upward with ropes and pulleys. Then they released it. Gravity did the rest. The ram struck the pile and drove it slightly deeper. Then the workers raised the weight again, and again, and again. The physics were effective. The labor was not. Every blow required another lifting cycle. Larger hammers produced stronger impacts, but they were harder to raise. Smaller hammers were easier to handle, but might require far more blows. Human power gave way to horses and mechanical hoists, yet the central bottleneck remained. The hammer spent much more time being lifted than actually driving the pile. By the 19th century, bridges, docks, railroads, and industrial construction were becoming larger, faster than traditional pile-driving methods could comfortably handle. The next breakthrough did not change what struck the pile. It changed how quickly the hammer could come back up. Steam power transformed pile driving during the 19th century. One major breakthrough came from British engineer James Naismith, who adapted steam hammer technology to pile driving in the 1840s. Instead of relying on teams of workers to repeatedly raise a drop weight, Steam could perform the exhausting part of the cycle. Naismith's pile driving machine used steam to raise a heavy ram and then allowed it to fall onto the pile. A contemporary industrial biography described a 3-ton driving block capable of delivering roughly 80 blows per minute, an enormous increase in repetition compared with older systems. The implications were immediate. A pile-driving crew could now deliver powerful impacts again and again without stopping to manually haul the hammer upward. And steam technology spread into several forms. Some rigs used steam engines to operate hoisting drums that lifted conventional drop hammers. Others used steam directly in specialized pile hammers. Either way, the rhythm accelerated. Lift, drop, impact. Lift, drop, impact. Pile driving stopped being a slow lifting problem. It became an industrial, pounding machine. But raw power alone did not explain why the piles could support enormous structures. For that, you have to look underground. A traditional steam pile driving rig was built around a tall vertical framework called the leads. The pile stood between them. The hammer traveled vertically above it. A steam engine powered a winch or hoisting drum. Cable ran from the drum over pulleys near the top of the rig and down to the hammer. The operator raised the ram. At the correct height, it was released. Gravity accelerated several thousand pounds of iron toward the pile head. Impact. The pile moved downward. Then the winch pulled the hammer back up. A crew repeated the cycle until the pile reached the required depth or developed enough resistance. Historical American projects show just how repetitive this could become. During railroad construction in Oklahoma around 1901, one large trestle required more than 400 piles, and records described each pile taking roughly 60 strokes from a 2.5-ton hammer. That meant thousands upon thousands of heavy impacts for one structure. Other machines used steam hammers that shortened the cycle even further by using steam within the hammer mechanism itself. But every design depended on the same fundamental idea: convert repeated vertical impacts into downward movement. The machine did not dig a hole first. The pile created its own path. And as it descended, something important began happening along its sides. This is the part that makes pile foundations more interesting than they look. A pile can support weight in two main ways. Sometimes its lower end eventually reaches a strong layer capable of carrying the load. That is end-bearing. But a pile can also develop resistance along its surface. As it is driven through soil, the surrounding earth grips the pile. Friction and interaction between the pile and soil can transfer structural loads along much of its buried length. That is why a pile does not always have to rest directly on bedrock. Drive enough piles into suitable soil, connect their tops with a foundation or pile cap, and the weight of a structure can be distributed across the entire group. A piece of timber that seems unimpressive above ground can therefore become remarkably useful once 30 or 40 feet of it disappears underground. And because the foundation was hidden, most people never saw the scale of what was being built beneath them. The visible bridge might begin with hundreds of invisible columns. The visible pier might stand on an artificial underground forest. Steam pile drivers simply made that forest faster to plant. Pile drivers became especially valuable around bridges and waterfronts. But that created an obvious problem. How do you operate a tall, heavy machine where there is no dry ground beneath it? Put the machine on a floating platform. Barge-mounted pile drivers allowed crews to position the hammer over locations in rivers, bays, and harbors. The rig could drive timber directly into the bottom, while boats repositioned the platform for the next pile. On land, rail-mounted pile drivers could travel along construction routes as bridges and trestles advanced. The machine became mobile infrastructure. At Nebraska City, for example, historical engineering records describe timber piles being driven through sand with a steam pile driver during bridge construction. When the machine's first boiler proved inadequate, a Northern Pacific locomotive was parked nearby and used to provide steam. That image captures the industrial logic perfectly. If the pile driver needed more power, bring an entire locomotive. Pile driving rigs could now follow railroad construction across wetlands, stand on temporary trestles, or float beside waterfront projects. The hammer was no longer waiting for construction to come to it. It went wherever America wanted to build. Despite its simple principle, pile driving required careful teamwork. Before any hammering began, workers had to position the pile vertically inside the leads. A long timber could be awkward to control, especially on water or uneven ground. Then came the driving sequence. The operator controlled the steam or hoisting equipment. Other workers monitored the pile's alignment. If the pile began moving at the wrong angle, the crew might have to stop and correct it. They also watched the pile head. Repeated impacts could crush or split timber, so protective caps or rings might be used to distribute the hammer's force. Then there were the cables, winches, boilers, and suspended hammer itself. Everything operated under load. Communication mattered because the people guiding the pile often stood far below the operator and close to the work. The machine could deliver thousands of blows during a project. Every one depended on the hammer traveling exactly where engineers intended. Pile driving looked like brute force, but controlled alignment was what turned brute force into a foundation. By the late 19th and early 20th centuries, pile drivers were appearing wherever transportation infrastructure expanded. Railroad bridges, timber trestles, industrial docks, urban waterfronts, wharves, warehouses, highway bridges. The numbers could become enormous. During one railroad project around Ardmore, Oklahoma, a trestle more than 1,000 feet long was designed with over 400 piles. Contractors brought additional pile drivers onto the work because one machine alone could not finish quickly enough. In California in 1922, construction records for the Carroll Overhead Bridge describe pile driving with a 3,000-pound steam hammer. When that hammer was removed, work stopped until another, this time weighing 3,600 pounds, arrived. That reveals how important the machine had become. The pile driver was no longer just another tool on the site. It could control the schedule. No piles meant no foundation. No foundation meant no pier, bridge, or structure above it. America could manufacture steel beams faster and move construction material farther than ever before. But before those structures could rise, someone still had to hammer the ground first. Steam eventually lost its advantage. Boilers required fuel and water. They needed time to build pressure. Pipes, valves, hoists, and steam machinery demanded maintenance. New power systems offered easier alternatives. Diesel engines replaced many portable steam plants. Electric motors improved lifting and control. Later pile driving technology introduced diesel hammers, hydraulic hammers, vibratory drivers, and increasingly sophisticated equipment capable of installing timber, steel, and concrete piles. The machinery changed dramatically. The fundamental objective did not. Take a long structural element, position it precisely, drive it into the earth until the foundation can safely carry the required load. Some modern systems hammer, others vibrate. Some press piles downward, but the construction challenge that created the steam pile driver never disappeared. Cities still build along rivers. Bridges still cross unstable ground. Ports still extend into deep water. And when the surface cannot safely carry what engineers want to place above it, construction still goes downward first. Most steam pile drivers eventually disappeared because they were working machines, not monuments. But a few survive. At Channel Islands National Park, the National Park Service preserves a historic wooden pile driver that was brought to Santa Cruz Island to repair a pier during World War II, and was later used again during pier reconstruction in 1987. The machine is now an artifact. The idea behind it is not. Every day, people drive across bridges, walk along waterfronts, enter warehouses, and stand on piers without seeing the foundations beneath them. That may be the real legacy of the pile driver. Its greatest work was designed to disappear. The hammer stayed above ground, the piles vanished below it, and once the construction was finished, almost everything the machine had done became invisible. America's bridges and waterfront cities did not simply rise into the sky. Before they could rise, they first had to be hammered into the earth.